Welcome to the Armstrong Memorial Lecture. I'm Debashis Mitra from the Electrical Engineering Department. And I see people streaming in, but we're a bit tight on time, so let me begin. By just telling you a little bit about the man which this lecture series honors, Edwin Howard Armstrong. So he joined Columbia as an undergraduate in the Electrical Engineering Department, and he received his degree in 1930. He was mentored all along by Michael Pupin, a very substantial Renaissance man on his own right, who had collaborated with Thomas Edison. So Pupin was actually one of two electrical engineering faculty members when the department was formed in 1889, 135 years ago. So Armstrong graduated in 1913, and stories have it that upon his graduation, he hung an antenna from Philosophy Hall, Havemeyer to Sherman Halls, and absolutely blew Pupin away by demonstrating that he was picking up signals from as far away as Honolulu. So, Armstrong was a scientist and an engineer, a faculty member of the Electrical Engineering Department, a major in the Signal Corps in the U.S. Army serving in France during World War I. And in fact, he had one of his major revolutionary ideas in the field. At his time, in the early 20th century, the standard for radio was amplitude modulation. And AM radio was very prone to static. And there's this memorable quote by John Carson, a very famous Bell Labs scientist, which goes like this: "Static, like the poor, will always be with us." Now, Armstrong proved him definitely wrong with his frequency modulation. So in his lifetime, Armstrong had about 5 revolutionary ideas. And they included wideband frequency modulation, FM multiplexing, and super heterodyne receivers. So he was, one of the major inventors of the 20th century. And his work laid the foundation of wireless communications and paved the way to 5G. In fact, there's no doubt at all that some form or other of his inventions resides in your cell phones. So, with that, let me just move on to the main business of the day. And it's a great honor to welcome Professor Mung Chiang, who is the 13th president of Purdue University. Before taking on the presidency, he was dean of the College of Engineering at Purdue, and even before that, professor of electrical engineering at Princeton. And while at Princeton, he initiated several innovative relationships and projects with industry. And he also started this Edge Lab and founded several startups. He serves, in 2020, he served as the Scientific Science and Technology Advisor to the U.S. Secretary of State. And he serves now on the board of the U.S. Foundation for Energy Security and several other companies' boards. Now, Professor Chiang has received numerous awards, and it's too many to enumerate exhaustively, but I'll just mention a few. He is he has been elected to the American Academy of Arts and Sciences, the National Academy of Inventors, and the Royal Swedish Academy of the Engineering Sciences. So let's welcome Professor.
Good afternoon, everyone. Thank you so much, Debasi, for this honor and very kind invitation. And I have known Debasi as a friend, collaborator, and a mentor for many years by now, following your pioneering work and leadership from Bell Labs all the way to Columbia. And I've also long been an admirer of Columbia engineering, including many colleagues and collaborators over the years in EE, in CS, in ORIE, and in fact, a couple of the students who came out of Columbia were then either my PhD students or postdoc at Princeton back in the days, and who have moved on to their outstanding academic career in their own rights as well. So it's great to be here, in particular to be standing in the shadows of all the previous lecturers of the Armstrong Memorial Lecture. And what an incredible story that you just summarized for all of us here on what Armstrong was able to accomplish as an inventor with the kind of impact that inspired all of us. And among those who were previous invitees include my Stanford professor, Tom Kyleth, from whom I took the course on linear estimation and control. And so it's an incredible honor to be here. But I have to say this talk is going to carry perhaps 3 surprises for all of us. I'll tell you the first 2 surprises. Surprise number 1 is that it's actually not my research field. I wanted to talk a bit about my own research field, which would be edge compute and 5G, 6G networks. But then I realized in today's environment, a talk on a national imperative like the CHIPS and Science Act and the CHIPS renaissance in our country perhaps would be even more appealing to a broader audience in engineering. But I've got great mentors and instructors back at Purdue, including Professor Mark Lundstrom. And if you have any tough questions about semiconductors manufacturing, please go ask Professor Lundstrom. And he and I together prepared this deck for this occasion, and I have been learning so much from Mark. And he, along with a whole group of outstanding colleagues at Purdue in engineering and science and business, in particular, the task force on chips at Purdue, led by Professor Lundstrom and inclusive of 30-plus faculty members. Some of the leaders are listed here. So this really is the talk prepared by them and honoring and reflecting their outstanding academic and societal work. So that's surprise number 1, that I'm going to give a talk that's not even my talk. The surprise number 2 shouldn't be surprising to all of you, that my day job these days, I still do some research on weekends and holidays, but my day job, I'm paid to do one thing and one thing only, and that is to brag about Purdue. So this talk is for a general audience about the roles that a research university can play in the CHIPS age in America, but I have to give some concrete examples, and I shouldn't give examples from other universities. So you're going to see some, like YouTube commercials you cannot click past, so you're going to see a bit of that. Please bear with me. I'm, doing what I'm paid to do. I'll save the third surprise towards the very end. But first of all, let's again recollect and honor what Edwin Howard Armstrong did. This is a picture, I guess, right around the time that he invented FM. And of course, even when he was a student here, a century plus ago at Columbia, he was already a pioneer in a topic relatable to today's conversation, radio circuits back in the days. Well, there's no transistors, no MOSFET, FinFET, there's no TSMC manufacturing process. But yes, there was circuits, and there was radio, and he was a pioneer there. Now, fast forward about 25 years or so to 1960 now. So Fred Terman is a hero of mine, perhaps of many of you as well. How many of you have heard of Fred Terman, by the way? Yeah, well, I guess there's a generation gap here in the room. So you all know Edwin Armstrong, for whom this lecture series is honoring. But also, Fred Terman is another giant of his time. He's widely recognized as the father of Silicon Valley in the 50s and 60s. And he was the Dean of Engineering, Provost, and Acting President at Stanford University, my alma mater. And he's actually a Hoosier. He's born in the state of Indiana, where Purdue University is located. And then he moved to California as a kid. And then he went on to do amazing work during World War II, in this case, serving the country, and then really built out Stanford engineering and then the whole university and the ecosystem to the very best one could imagine. There was no Silicon Valley before Fred Terman. So Terman, towards his retirement, actually, in the 60s, he came back to Chicago, the Midwest, at the 16th National Electronic Conference, and he said the following, that during the last 2 decades, electronics, I guess, especially since Bell Labs' 1947 transistor invention, has become one of the most exciting industries of all time. This new electronics, by that, in 1960, Fred Terman meant the integrated circuits using particularly MOSFET. Lives close to the frontiers of science and requires a high level of technical competence. It grows by the development of new products. It's characterized by the transistor and other solid-state electronic devices. I'm going to keep quoting Terman for a few more rounds later, but this is how he started his remarks 1960. Just about a month or so prior to his remarks, Robert Noyce demonstrated the first monolithic silicon IC, what we would refer to as chips these days, on September 27th, 1960. And this is the picture that NASA used. It is the Apollo spacecraft controller, and you see the logical IC right there. Now, Terman said that in the new electronics, education and educational institutions, such as Columbia or Purdue and Stanford, have a new and increasingly important role. So it is in the spirit of Terman's remarks 64 years ago in autumn that I am now relaying perhaps some of those important roles that he was referring to. So industry is discovering that for those types of electronic activities that involve a high level of creativity of a scientific and technological character, it is more important to be located near an educational institution, near a center of brains, than near markets, raw material, component supplier, transportation, or factory labor. Now, one could disagree with this statement to say, well, I kind of think it's useful to be near a market, for example, or near labor. But from my biased viewpoint, I very much like this quote, that when you are talking about the creativity that is constantly required to redraw the economic equation, you would like to be near a center of brains. So education is a natural resource of first importance to that part of the electronics industry that is growing through creative activity. So you see education institution, you see industry, and Terman was claiming what is perhaps now obvious, at least to all of us here in this auditorium today, first importance level when it comes to the interaction between the two. So Terman then went on to outline 5 roles of a research university in the new electronic age. A source of talent, that's the most important raw material, the most important supply chain. A source of ideas, because they have to rewrite through innovation the economic equation. A source of faculty experts to aid industry with its problems. Now that's a very specific way to think about one of many roles that a faculty member can play. Not the only one, but certainly an important one. Provider of educational opportunities for employees, and in a tangible but very real way, a university provides an atmosphere that stimulates creativity and makes a community attractive to scientifically minded individuals. Like all of you as students and faculty and research staff at Columbia Engineering. Now, that's 64 years ago. So if you think about this industry, this particular semiconductor and microelectronic industry, many things have happened since. For example, used to be a niche industry. Now the foundational technology for the entire digital economy, digital society, and digital lifestyle. The semiconductor industry supply chain has become specialized. You've got manufacturers that don't design and designers that don't make. You've got special packaging companies, and you've got still some that try to do both. And it has become global, whether they're located in like-minded countries or otherwise. Now, the Moore's Law, now famous, sort of slowing a little bit by the slope, but the shape is still there. And what the experts in that area would call the fourth wave of semiconductor technology is just beginning. We'll see how long that can sustain Moore's Law. And then, very recently, 2 years ago, the U.S. CHIPS and Science Act, a bipartisan act sponsored in the Senate by Indiana's senior Senator Todd Young and the Senate Majority Leader Chuck Schumer, passed and signed into law. So first, let's take a look at this particular chart. It's the famous chart. There are many different versions of this. This is one particular color code. So when I was taking a class from Mark Lundstrom and many other experts at Purdue, they taught me how to read this chart. So first of all, the y-axis is logarithmic scale, so that's impressive. And then you see 1960 from Fred Terman's speech, which is only 2 weeks after Robert Noyce's demonstration of IC, all the way to now, 2024, projecting into 2032. So those dots are the technology nodes, and they sort of look like a straight line on the log graph. That's impressive growth there. The first wave, you make the transistors smaller, and you pack more of them in a given area. That gave us all the way, from the first one or few, all the way to 10 to the power of 5. So that's impressive. By the 80s. Then people realized that the interconnects by aluminum is not good enough with transistors of this kind of miniature size. So they changed over to a different material, to different metal, copper metallization. Sounds easy, it's difficult material science, difficult chemistry and physics, and then difficult manufacturing process. But that lasted for another decade plus. Now you are 10 to the 7th. And then you got to 3D, in particular FinFET, and that gave you another 2 decades of growth, all the way to 10 to the power 11 now. So just think about it, from 10 to the power 0 to 10 to the power 11 within a span of a lifetime, or roughly 60 plus years. That's incredible. It's hard to imagine, even in the age of science and technology, what other technological areas can grow in a sustained manner, non-stoppable, through different types of innovation over the years with this kind of 10 to the power 11th order magnitude growth. In fact, if you look back, this is the 1947 transistor invention, and right before the IC demonstration was the invention of MOSFET by two other Bell Labs inventors, and that made the transistor commercially viable. Back then, they were thinking, all right, I got a few transistors together, that's pretty cool. And nowadays, it is MOSFET and its variants is the most human-made engineering artifacts ever in history. I forgot exactly how many there are, how many transistors. 10 to the power 23, I heard one number. In any case, that number is growing like crazy, given how many there are on one single chip and how many chips are being made and used these days. from mobile devices to, of course, laptop, of course, to cloud, to AI these days and more. So that's incredible. And also, if you look at the whole stack here, from materials and chemistry, and we indeed need new types of understanding of chemical process as well as new materials, to new physics. For example, at Purdue, we have great faculty in spintronics, and then the design and the simulation and the modeling of device and circuits out of the physics. And then you look at the integration, including manufacturing and design and test assembly packaging steps along the supply chain. And then you look at the whole architecture, including the non-von Neumann style architecture, computing memory these days, or you look at neuromorphic computing, another strength out of many at Purdue. And then you think about the overall software hardware co-design. How can you design a piece of hardware that enables computation and fit the algorithmic need, while at the same time optimize the algorithms so that they fit the underlying physical substrate's unique properties. And some of the areas we're going to touch upon later in the hour include systems in packaging, particularly advanced packaging through what folks would refer to as heterogeneous integration and advanced packaging, HIAP. There's a lot of work going on across the country, in particular at Purdue, on advanced packaging and 3D and heterogeneous integration. Now, in that manufacturing process these days, not only chips enable AI, but AI in turn enables the design of chips and the production, manufacturing, and assembly of chips as well, including the use of AI-assisted tools and digital twins to accelerate manufacturing, which then make the chips for AI even better. Well, one other thing we just mentioned, a little over 2 years ago, the U.S. Chips and Science Act was signed into law. Roughly, there are two components. One is $39 billion of government grants from the federal to companies for incentives in onshoring or reshoring manufacturing capacity of what they call leading nodes, so very small feature size, or the legacy nodes, larger feature size, but nonetheless useful for other industries beyond iPhone. And then $11 billion is for R&D. Now, for a lot of professors, this part sounds particularly interesting. Now, part of that $11 billion is the $2 billion that's already been decided by Department of Defense Microelectronics Commons program, and there are quite a few other programs rolling out. We'll go through them briefly in the coming minutes. Now, part of that is, yes, reshoring the production, the making, the manufacturing component of it. But the other part is to accelerate innovation through fundamental research translation, but also cutting across all of them the importance of workforce. So now we're coming to the subject of the talk. What roles can a research university play in this renaissance or revitalization of semiconductors in the United States? Well, Terman outlined 5. I'm going to bundle 2 of them into workforce and retraining of existing workforce, 2 of them into the research and industry collaboration, and then maybe talk a bit about this fuzzy, warm, but really important notion of an ecosystem of creative environment that fosters innovation. So now here comes the commercial part. Well, it's a, yes, advertisement for Purdue in particular, for the College of Engineering at Purdue. We care deeply about all the colleges, but since this talk is mostly driven by engineering faculty's work, so I'm going to just spend 1 minute here. Purdue Engineering, what we call excellence at scale. Right now, we are number 1 in the U.S. by market demand, number of applicants to undergrad and grad programs in the college, number 1 producer of engineers. We have right now 19,305, that's very precise, somebody wrote that. I hope those students dropped out since. Of fall 2024 enrollment, including over 13,000 undergrads, more than 5,500 master and doctoral students. So the incoming undergraduate class alone this year is approaching 4,000. So you see the scale. What about excellence part of it? So we have 16 ongoing, federally funded, 10 million or above level research centers across many areas, not just in semiconductor, the topic of today. Well, the highest ever top 5 ranked college of engineering in terms of size ever in history. And right now, I believe there are 7 undergrad engineering programs in the top 10 in America and 9 grad programs in engineering among U.S. top 10. And, well, that NASA chip for Apollo program, well, one of the Apollo program's iconic heroes is Neil Armstrong, who is a Boilermaker, as we will call, Purdue alum from engineering. I used to have my office right there passing by this statue of Neil Armstrong all the time. So now, don't worry if you think that's not enough advertisement for Purdue. There's more to come. You won't miss it. So now, workforce. So there are 2 kinds of workforce. First of all, there are those that are employed writ large, including construction and installation labor. And there are not any construction installation. These are highly skilled laborers, given the kind of buildings you need for manufacturing of chips and the equipment you have to install. Some of these are hundreds of millions of dollars per equipment, and you got dozens of them. So you better make sure that you don't screw up the way that they're installed. But also there are the semiconductor engineers that we need. And according to SIA and some other statistics, by the end of the decade, our country alone would need 50,000 more, delta, more semiconductor engineers. Now, it's slightly better than it looks because it doesn't mean it must be somebody holding a degree from Columbia or Purdue or Stanford saying, oh, my degree says Bachelor of Science in Semiconductors. It could be Bachelor of Science in Electrical, Material, Chemical, Mechanical, Environmental, Computer, etc., in physics and chemistry, as long as you have been equipped with certain level of knowledge about semiconductors, maybe a minor degree or certificate in semiconductor manufacturing. So it doesn't have to be a dedicated undergrad degree. And also would include those who are master level, those who are associate level, and also those who are online degree and certificate holders. And indeed, Purdue has been working by firing all cylinders at the same time to develop the fresh new workforce needed. Now, one university alone cannot be producing 50,000 to one industry in this decade, but we hope that we ourselves can produce thousands of talents to this industry this decade, and then the curriculum and the consortium and the partnership that we form with many other universities will produce tens of thousands more. So when people ask me, so there was a Wall Street Journal reporter who asked me about a year and a half ago, so how many do you think you can produce out of 50,000 as the demand? I say, well, I think it's going to be a 4-figure number, a steady state per year. And then the reporter came back to me and said, just want to verify. When you say 4-digit, you mean 1,000 or you mean 9,999? There's a difference. I say, yeah, we'll be somewhere in between. But I think that it's going to take the whole village. One university, no matter how big the excellence scale might be, can only do so much. But together, we can do quite a bit. So we ask ourselves, workforce, 3 questions. 1, will the students be interested? So if you are not interested, it doesn't matter how much we can offer you through new degree programs. 2, how can we then prepare you for this new era of microelectronics and semiconductor? And finally, how can we ensure that you're also able to relearn and retrain yourself over the next 40 plus years? We start with awareness. So one of the largest student-led job fairs in the country is at Purdue, and it's called the Industrial Roundtable, 400 plus companies. So for the first time this past 2 years, we've got a huge number of semiconductor companies, 34 of them. And you see Dr. Lee, VP for Advanced Packaging from SK Hynix here, giving a talk to an auditorium packed with students interested in co-op, intern, and full-time employment opportunities. We also raised awareness through a new course called Engineering 103. It's an interactive industry-led lecture series with speakers from many different companies. And 200 plus first-year engineering and some science students would take this class per semester and get a first-hand experience. We also have a third channels, if you will. About 100 students this past summer went through the STARS program, which is a hands-on learning experience with industry, a summer co-op experience. And the demand, however, is actually 1,000 applicants from our own students. We do not see the scale of the demand. We only lined up about 100 such paid internship opportunities with our corporate partners. But next year, we'll try to take care of a larger percentage of the demand. We also have something long-standing called VIP, vertically integrated projects. These are basically taking a course that's really a research projects and do that in a team environment at Purdue Engineering. Starting freshman year, and you work with sophomores, juniors, and seniors in one single team. So we've got a system on chip design team in VIP now, a semiconductors track in the clean room. I'll come back to that in a minute. And within 2 years, since we rolled out semiconductor degrees program in 2022, the student enrollment have gone up by 7x, and there's no stopping anytime soon in the horizon. So if you think about what we call SDP, the Semiconductor Degrees Program, right now, after 2 years of pilot launch, we have 550 students enrolled. Some of these are doing the undergrad minor degree or certificate in semiconductors. Some are master students, and the master students could be taking a typical MSEE, for example, or MSME, but with a concentration in semiconductor. Or they could be taking a whole master degree in semiconductors, because there's enough material to go through the whole supply chain. Think about it. You can learn about the materials. You can learn about the tools, the hardware and the software tools needed. And then you can learn more about the design of the chips. Then you learn more about the manufacturing of the chips. Then you learn more about the packaging, including advanced packaging and heterogeneous integration. So easily you can see a master degree covering basically the whole supply chain, and then maybe you take 1 or 2 business school classes on the global supply chain issues, focusing just on semiconductors. We want to provide enough technical depth, whether they are the undergrad minors or the master degree students, but also want to provide breadth so that you understand enough about sustainable materials, thermal management. You know enough about manufacturing, you know enough about reliability, and then there are some other non-technical skills we sprinkle throughout the degree programs, such as communication skills, teamwork, ability to quickly learn new things. Then we took SDP online. Now we don't have undergrad degrees online from Purdue. Purdue Global offers that, not in this particular area, but we do offer online master degrees, online certificates. So as mentioned, you can do a whole master degree online in semiconductors from Purdue now, or you can do it residential in a typical, or online, a typical degree program with a concentration. There are graduate certificates, there's all the way to a free first course in Semiconductor Fabrication 101. So all of you, welcome to just Google that and then log on, and it's free. And then everything else you have to pay. So you've got to pay at some point. the rankings aside, I think what's interesting is that we believe in the coming years towards, say, 2030, the SDP online component is going to outgrow the SDP residential. And this is where the existing workforce, working professionals, they may have a master degree from, say, Columbia in mechanical engineering. And then 20 years later or 15 years later, she would like to switch field to semiconductors from, say, transportation sector. And then she would say, I'm going to go take a master degree in semiconductors. I know enough about engineering and design, but I'm going to switch gear now. So how can you retrain existing workforce or just upskill those who are already in the industry sector and be able to keep up with the evolution of the new technologies? So this is the total educational experience. You've got the breadth, you've got the depth, and you really would require both a core curriculum that's grounded in the fundamentals, grounded in the classic textbooks and the new generation of those textbooks, but also give them a lot of hands-on experience throughout the year, in summer, with industry. So if you think about what we've experimented over the past 2 years with the workforce development, we have quite a few observations, one of which is igniting student interest is not the only challenge. Initially, we thought, oh, gee, everybody just wants to do AI, ML, they just want to work for Google and program, and they know how to code, and they are not interested in something physical and hardware-oriented. Well, it turns out, at least at one university, that wasn't the case. There's more demand than we could supply anyway at this moment. But how do you respond to the surging student demands? That's a challenge on the supply side. We need to provide a lot more opportunities for experiential learning, developing practical skills, and we need to work with industry for that. Another interesting one is you have to work as true partners, not just take the money and say thank you, but also get them to help teach some of the courses, get them to help design the lab layout. And then you also go out there to talk to their existing employees on what they need so that your online offering is relevant to them. Now, some of you may know this SEEC is the Electronic Education, Semiconductor Electronic Education Committee decades ago, and they produced affordable classic textbooks. And we're wondering, perhaps it's time for a new set of SEEC-style textbooks with the kind of new knowledge being generated and make it very affordable for anyone to learn from that. Well, switching gear now to research. So Fred Terman also highlighted the importance of generating new ideas and the importance of faculty working with industry to deploy those ideas. So the dissemination of knowledge, but also the discovery and deployment of knowledge. You may have heard of this term, lab to fab. So from a university lab where fundamental knowledge is discovered to a fab, which generally would denote the industrial scale, S-scale production, or at least a fab towards S-scale production. But there's a huge gap now. Even the most well-equipped university labs in semiconductors, and Purdue has one of the largest and the finest clean rooms among American universities, but even those pale in comparison to what industry is using. Right? The level of investment in the hardware is just staggeringly different now. So how can we accelerate the pace of innovation and be relevant and useful from within a university? I was wondering, where's the rest of my commercial slides? Here's one. So, there are a few of these research centers and institutes in the areas of chips at Purdue, and I'll just highlight some of them. One is the physical space called Burke Nanotechnology Centers, 25,000 square feet of clean room, supporting 300 resident researchers. It's been there for 20 years, and recently we provided another $50 million to upgrade the clean room there. We founded what's called Atala Institute. Now, who is Atala? I'll come back to that towards the end. Please remind me. But this is an institute for advanced system integration and packaging. So we've got faculty addressing power, thermal, signal integrity, mechanical reliability, new material in heterogeneous integration age. We also welcome quite a few others, partners. I'll come back to IMAC, which is headquartered in Leuven, Belgium. For 40 years, they have established themselves as a multi-billion-dollar research hub, at least in Europe, if not the world, with universities and industry. So they just opened last year their U.S. Research Center on Purdue campus, working on a few important topics, including co-design, sustainability, yes, again, advanced packaging and new material. Well, we are one of the recipients of the Doty Microelectronic Commons, as alluded to just now, with Indiana, but also Illinois, Michigan, that part of the Midwest hub. TSMC and Synopsys, and now MediaTek, funded CSME, which is on secure microelectronic ecosystem. We recently just received a round of support from DoD on Institute for Chips and AI. Again, chips as an enabler of AI, obviously. Compute has to happen somewhere, but also AI benefiting chip design and manufacturing. SK Hynix, I'll come back to that. They're establishing an advanced packaging facility, but also as part of that, a research center. And there's something that's sort of a hidden treasure, a national hidden treasure, if I may, called NanoHub. It's been going on for more than 20 years. It provides an online scientific collaboration and simulation environment. And this online platform has attracted more than 1 million scientific users a year, and now they created Chips Hub for open source tools to be made available within this online simulation environment. And the list goes on, but you get a sense of the kind of research centers we're talking about here. Now, what does the industry say? Well, one of the organizations is called SIA, and they've been providing a lot of public domain feedback to the federal government, including the NSTC program. So National Semiconductor Technology Centers program as part of the Chips and Science Act R&D side, that it should reflect the industry technology priorities, yes, align with the tech agenda and roadmaps of the industry, okay, and the infrastructure should aim to meet piloting, prototyping, and the scaling needs. These are three distinct needs. And the primary focus should be on maturing and scaling these technologies and move beyond early stage research. So there's a lot of modalities of industry, university collaboration and research. Now, workforce, we know more or less, we produce great students, you hire them as intern or full-time, and you've got existing employees, we provide online learning to complement your on-job training. So roughly people have no disagreement on what should be done. How to do it best, we try to improve and optimize all the time. But when it comes to research, there's a bit more of a philosophical debate. For example, how much should be fundamental research versus applied research? But in my mind, it's sort of a non-issue debate. I don't want to belittle the importance of the topic, but as an individual faculty, it's your individual choice. Right? That's the beauty of American academia. It's your choice if you want to be more theoretical, more applied driven as you see fit. As an institution, we should say yes and yes to both. It's not a zero sum necessarily. And one version is industry-driven, the other is industry-informed. Right? Industry-driven is more of coming from industry into academia to drive the research agenda. And industry-informed is more about, yes, I'm listening to you, I'm listening, but here's what we are creating. Maybe you have not thought about that on the time scale that you care about as a company and feeding back. Both, again, are important. So here is a partial list of the industry partners we have related to semiconductors at Purdue. There are well over 30 of these companies, 2 years ago, we called their CEOs and say, well, we are doing the workforce side, but we're also doing research. Would you want to partner? And then they sent their CTOs or equivalents or VP of engineering to form the Semiconductor Degrees Leadership Board, which now also start to advise our university and faculty students on the research innovation front as well. So we meet twice a year. In the fall, we'll be in Indiana, in West Lafayette, and in spring, we'll be in Washington, D.C. So without going through all the names of the companies, you see a great mix of companies. There are a couple of universities represented as well. And some of those make chips, some of those design chips, some of them do both. Some focus on packaging, some are tool makers, some are material providers. Again, it covers the whole supply chain there. Now, all of you have heard of this valley of death. It applies to translational impact and entrepreneurship. It also applies in this case as you go through stages of innovation. There's no precise scaling on the x-axis, just warm and fuzzy, let's say. Roughly, it goes towards the right with more mature TRL higher levels, so technological readiness level going from level 1 all the way to 9 and more. And then the kind of investment that you need. Now, clearly, private sector, whatever CHIPS and Science Act provides, R&D and industry grants are just trying to level the playing field. It cannot be the sole source of support or the majority of the support. Eventually, the private sector will be technologically most ready for deployment and by far the largest investment. This is probably log scale as well. Now, but in between university fundamental research and the private sector taking over, in between, right now we're looking at a collection of different mechanisms out of the CHIPS and Science Act. The DoD Common Hubs I mentioned, Manufacturing USA Institutes. Right now there's one going on in the area of digital twinning. There's the NSTC as mentioned in research, but also NSTC programs, and then NSTC prototyping facility. This would be a national facility. Now there's ongoing debate as to exactly where, how much. And then there's the NAPMP, which is on the advanced packaging side, pilot line. So now the hope is that with all these different programs collectively out of Department of Commerce, Department of Defense, Department of Energy maybe, and National Science Foundation, a little bit on this side, there will be adequate connective tissues between fundamental research and industry scale deployment. Now, one particular area I want to highlight is what SIA said, to maximize the impact of finite and public investment. I guess, all investments are finite, but not only finite, we know exactly how much that's in the R&D budget. NSTC should upgrade a few. Now, whether that few means 1 or 10 or some sweet number in between, well, I have my own biases, and I think Purdue should be one of those, whatever number is, but a few accessible state-of-the-art facilities. State-of-the-art, not just academia scale, but industrial scale, as in leading university and research centers. In other words, going from the TRL levels 1 to 3 to TRL level 7 to 9, this valley of death with a bridge facility. Right? So bridging lab to fab, and in this case, physically investing in a handful, pick a number you like, 3, 4, geographically diverse, located throughout the country, where nearby ecosystem and the driving distance universities can come together to have those that are not owned by a single company, but also much more state-of-the-art than what we currently have at a single university. So I am proposing, we are at Purdue proposing Burke Nanotechnology Center to be one such candidate of a potential bridge facility. As mentioned, 25,000 square feet of clean room inside, a 200 1,000 square feet of lab space. University ourselves have been pumping past year $50 million to upgrade the facility. But to get it to the bridge facility, you need order of magnitude bigger level of investment to become an open innovation ecosystem shared by others. One more. We're coming towards the end, so don't worry, there are only that many finite number of commercial slides coming up. Over the past year, if you look at the CHIPS-related R&D program, Purdue competed for, and received, along with partners, quite a few of those. I won't have to read through all of them. But if you look at what's coming up, though, that is even more exciting. The vast majority of the $11 billion of the CHIPS R&D program, plus non-CHIPS funded programs, the vast majority are actually coming up in the coming months and years. So within West Lafayette, Indiana, we are all trying to get ready to compete along with partners for all of these. Now, a special shout out to Netcast, which is a nonprofit affiliated but not part of the federal government, and led by the inaugural CEO, Deidre, who used to co-chair Purdue's Semiconductor Degrees Leadership Board, coming from Synopsys. And over the past 6 or 8 months or so, it's been, she, along with her team, and then the Department of Commerce, have been doing a great job in launching new programs and facilities across NSTC, NAPMP, Manufacturing USA institutes, and other workforce development activities. Now, the third and last component, back to Thurman's list of roles a university can play, is this notion that a university can help create a physical hub of ecosystem whereby other universities and companies can come together. And what good can come out of it? Well, I don't exactly know. And that's the beauty of it, is that they're going to bounce off of each other ideas, and you're going to have people who run into each other. And then they're going to create something we cannot foresee today, that stimulating environment for creativity and making a community attractive to scientifically minded individuals. So 2+ years ago, Purdue welcomed both Secretary of State Blinken and Secretary of Commerce Raimondo to Purdue campus to take a look at what we were hoping we could build in the coming years into such a hub of clusters and ecosystem. And there's Governor Eric Holcomb, Senator Todd Young, one of the architects of the CHIPS and Science Act. So I'm just paraphrasing the secretaries here, and this is all public record. You can fact check me. The Secretary of State said, "This is, meaning Purdue, the most exciting human fab that I have ever seen." And some people say, "Oh, he's exaggerating." I said, "No, he's not exaggerating. He meant what he said." And Secretary Raimondo said, "I have to tell you how blown away we have been with what we have seen here at Purdue. Incredible, from lab to fab." Now, this ecosystem doesn't mean, therefore, we only work with those who are already in West Lafayette. It's all about growing that ecosystem, including working with quite a few like-minded countries, such as, say, Japan. So at the end of G7 meeting last spring in Hiroshima, we had the signing of the U.S.-Japan partnership, working with a number of universities and companies with some joint funding. And this is with India's semiconductor mission, which has kicked off the new wave of semiconductor investment in India. And you can look at the list of the partners that we have created with our faculty's work. Now, I want to highlight two. One is IMEC, as mentioned. 40 years ago, the Flanders government in Belgium had the foresight to provide seed funding. And again, 40 years ago, nobody perhaps saw how important the semiconductor is going to be. And this became a consortium for multiple universities and then companies. And now, 40 years later, it has provided an interesting collaborative model IP arrangement, facility sharing arrangement, workforce coming back and forth between universities and industries, all kinds of models. So I visited them a couple of times, and they would like to set up a American branch, and in particular, a research center in the United States. So Purdue was able to compete for that site and bid, and were able to win it. So this is coming from December last year, when the CEO of IMAC, along with the government leader, the Flemish minister, president, coming to Purdue to ribbon cut to this new R&D hub by IMAC, but located on Purdue campus. And then earlier this year, so now we're fast forwarding quite a few steps. So this is, again, 2 years ago. This is 2023 spring, and then this is late last year, and then this is 2024 now, in April, where the company headquartered near Seoul in South Korea, SK Hynix, announced that they are going to build a $3.9 billion fab for AI memory chip at Purdue on our campus. So while this is not the largest semiconductor fab in the country, I believe it's the largest located at a university. Now, we are not paying $4 billion to build it. It's not our facility. It is the industry facility. SK Hynix owns it. Now, the question is, they had many choices, 50 states and many other locations throughout all the states. So why Purdue? Now, they are the best to answer that question, but I would guess that one, for the workforce, and two, for the innovation capabilities, and maybe three, for a supportive and stable environment that they can thrive in many decades to come. So $4 billion to start with, and then we believe it's going to snowball, and then there's going to be supply chain companies coming in, the vendors, the tool makers will come in as well, located on Purdue Research Park. Now, what's interesting, by the way, is that this does two unique things for the American semiconductor revitalization. First, the products they're going to be making is called HBM, high bandwidth memory. It's the kind of memory that NVIDIA AI products will be dependent upon, and that's why they're doing so well. The other one is that it's focusing on advanced packaging, STEP, as mentioned before, which is sort of where the biggest bang for the buck many believe will be residing in the coming decade or so. So it completes that supply chain in two unique ways. Well, now if you zoom out to the map of the United States, other than Hawaii and Alaska, you look at this map here, and you see 7 dots. These are the CHIPS Act Program Office, regional semiconductor clusters. So you go from fab to lab, and now to clusters, to an ecosystem. And that's roughly where Purdue is, the Indianapolis campus, West Lafayette campus. And of course, you all know the upstate New York one. Now here's a same map, but different dots. These are the DoD Microelectronic Commons Hub, the research competition. About 80 applicants, and then 8 were selected, including Purdue as the leading university partner of one of the 8 winners. Now, between these two maps, this is not a test, but there are a few common nodes. One is in Arizona. One is Intel TSMC. One is upstate New York. Okay, IBM, Micron, Global Foundries, and so on. And then there's one in the Midwest, between central Indiana, where Purdue is at, and central Ohio. So if you zoom in now to one of these 3, namely the Midwest cluster, you see what we call the Silicon Heartland. So how many of you, by the way, have been to any of these states? Okay, great. You have to go to O'Hare to no. Well, you should all come visit us. There's a lot of great things happening. Let me just focus on one thing, which is the concentration of outstanding universities. I know there's a lot in New York City as well. I'm preaching to the choir here the importance of clusters. But yes, Purdue, but also if you look at, there are 20 R1 universities within driving distance of Purdue. 3 of the nation's top 10 graduate engineering colleges are in driving distance. 4 of the top 10 producers of bachelor's degree in engineering and CS. 3 of the top 10 producers of PhDs in engineering and CS, all within driving distance. And then there are 2 national labs, 2 defense microelectronic hubs, et cetera, et cetera. What we hope is that, yes, there's going to be maps like this, the reshoring of manufacturing and the revitalization of research in semiconductors throughout the United States. But selfishly, I'm going to zoom in over here and say that there's a lot in the Silicon Heartland because of the density and the concentration of the brains. Back to Thurman's message. So we're getting some national press and coverage, so people starting to pay attention to say, oh, what's up here? What's going on here, in the Midwest? They know manufacturing, I get it, but now they also seem to know something about microelectronics and semiconductors. But I want to wrap up the conversation here with a particular person's story. So this is another Boilermaker, and he's there roughly the same time, similar decade as Neil Armstrong, actually, as a PhD student. His name is John Atala, an Egyptian-American, received a doctoral degree in mechanical engineering, actually, from Purdue in the early 50s. Then he worked at Bell Labs. In 1959, remember, we were talking about MOSFET as the first commercially viable transistor. Well, that was co-invented by John Atala in Bell Labs. And then he started to build startup companies of his own and then ventured into cybersecurity and other areas too. Now, what's interesting is that in John Atala's story, of course, I'm biased, I picked a Boilermaker, but in many stories like his, you see all 3 flavors of that university's roles in a national narrative. Right? There's the workforce. He graduated from the doctoral degree program, went into the workforce. There's the research collaboration, Purdue and Bell Labs, especially back then in this particular area, driven by physics and engineering, had a lot of interactions. And then he went over to a different ecosystem, the Bell Labs ecosystem and the cluster, not far from where we are today. And now today we are trying to build a new ecosystem in a different part of the country. But you see all 3 flavors of the kinds of roles that a major research university can play exemplified in this, just like in many other cases. So now we believe that reshoring and re-energizing, both the making and the designing, both the deployment and the fundamental research of semiconductor industry, it is a national imperative these days for national security and economic security and job security. Now, we will succeed, but we cannot underestimate the amount of challenges in every aspect and along every step of the way. And university is not the only player here, but we believe that research universities got a very special and important role to play here in workforce development, in research, and in industry ecosystem building. So let me invite all of you to the next SDLB Semiconductor Degree Leadership Board meeting, which is also an open meeting. Last time we had to cut off at 200 participants, 175 companies or universities represented, in the Senate building in Washington, D.C. This is going to be in April, or the Midwest Semicon Conference, which is industry-led conference, but co-located at Purdue, coming up in April. Now, you may still recall, if you haven't fallen asleep yet, or started taking the free course, the Fab 101 course online, You said, wait, Mung, you said there's going to be 3 surprises. All right, the first one, this talk is now your area. Okay, we get it. We can feel that. And 2, that is a lot of Purdue talk. Yeah. We saw that. And what's the third one? So the third one I'll leave you with is that I think the most exciting thing of what we just walked through is not even just about semiconductors. Now, if you strike the word semiconductors, now, you say, well, now you tell me that after a whole hour. You strike that and substitute it with something else of equally important national narrative and movement. And you say, are there similar roles that the university can play? Not everything is portable, but some are. So I think what we're talking about here is not just for semiconductors. It's for, generally speaking, how can a major university like yours, like ours, like many others, frankly, that can play an important role along these 3 dimensions. But you've got to set ambition high. You've got to develop an execution strategy. You've got to find the right partners, and time is of essence here. When people ask, well, what are all these universities doing? There are many answers. This could be one of the answers. So it's not just about chips. It's really about many important national imperatives that we all have a role to play here. Thank you again very much. Yes, please.
I want to refer back to your comment about the major investment of upgrading foundries that are accessible to universities. You mentioned the Purdue one.
Yes.
Now, we know that foundry usually doesn't last long because you get one technology, very soon you're building the next one, and commercial foundries, they rely on the fact that they're going to build and manufacture and sell enough chips to recoup that investment and build another. University can't do that. So are we going to need chips 2.0 in 10 years from now, or is that actually a sustainable
It's a great
strategy?
question. Semiconductor industry is sort of defined by 2 cutthroat features. One is scale. You've got to have enough yield at a scale. But the other is speed. You are destroying your last generation yourself every so often, faster than many other industries. So now when you have scale and speed combined, it's very capital intensive. So it's a great question. My personal belief is will be like the IMAC model. Once the initial governmental support, federal or state level, drives the train forward, the future iterations should be primarily funded by industry funding. Once they see the benefit to participate as one member of an open innovation ecosystem.
But isn't the better strategy then to make commercial foundries accessible to university researchers and have them be driven by business, but still make it accessible for researchers to use them, just like we have open source software, where you have companies investing into open source software and contributing source code so that they can later get benefits, but also researchers use that.
Another excellent point. And first of all, a lot of startup companies, more than universities, are crying for access. They don't have the volume to be at the front of the queue, so they get dropped, and they need some access if you want the startups in this space to ever stand a chance. And furthermore, there is a valid alternative of turning some of the commercially operated foundries, whether it's for memory or logic, packaging or manufacturing, to become accessible. Now, one challenge, I can think of 2, doesn't mean it's a showstopper. One is that which company, and there's always the worry that, it's that picking winner or losers and so on. And the company may ask, why should I be the first? The other one is prioritization. If that commercial fab actually has commercial activities going on as well, then doesn't mean the university and the startups will be in the second-tier lane. You have to wait until that demand clears up. So both are concerns, but can be addressed. So I don't have a particular advocacy, say, it got to be a neutral third party or university hosted. If that route works, I think that could just be as useful. Okay. Yes, please.
So in terms of universities working with industry for innovation, another way to spend time at a university
Yes.
for longer than just
Yes.
teaching a class,
Yes.
and also vice versa, maybe having faculty spend time in industry.
Yes.
Do you think this is valuable, and if so, is Purdue doing anything to support that?
It's absolutely valuable because it's the who before the what. It's the trusted human bridge that carries the weight at the end of the day. One direction is a little easier. The university is letting faculty be there, especially in summer or during sabbatical, is more viable. The other way around, the most productive ones in companies probably would not be permitted by their supervisors to spend a substantial amount of time away at another place. But we could encourage them to become a resident for weeks. It's hard to imagine a whole year or half a year, but for weeks, as executive in residence or as tech leaders in residence. And then we certainly encourage our own faculty to spend time over in industry. Now, we have to sort out the IP issue if it's extended stay, and they're now co-inventing things, and who's paying for what part and who owns what. But again, doesn't mean it's a showstopper. There's a will, there's a way to do it. And Purdue is doing a bit more of the latter, but your question triggered me. I'm going to write a mental note in my mind now to go back home and investigate a bit more on the first direction.
I want to attest to that. I really personally benefited from that interaction to Berkeley. It really is very valuable.
First of all, wonderful talk. Thank you. Talking about IPs and what is not IPs, no? And talking for chips and systems based on chips. So IPs, new IPs, you build businesses, and so, as you said, I completely agree with you. New IPs are developed, they have their owners. But both, in order to develop many of these IPs, as well as to develop a workforce of students who, some of them at least, can work on very critical problems and be ready to join industry, increasingly we need them to work on more complex systems than what you can just as a single research group or even a group of like few faculty do in academia. So one way that some of us are thinking about this is that we should at least in part follow the open source model that has been so successful for software and do open source hardware. Not of the most critical new IPs, but a lot of the things around that you need, for instance, to build a system on chip.
Yes.
So what's your take with respect to open source? Because it could potentially create a zona franca where it's easier for university to not just educate students, but also collaborate across with industry, across industry, because you could use examples which are interesting enough even though they're not products.
So I believe in a practical view that's not one size fits all. Depending on where you draw the boundary of pre-competitive and where you draw the cost-benefit analysis. For everybody to come to the party, it got to make sense for them, for every one of them, right? So they got to see I can derive more from this interaction than I'm putting in there or giving up in walking into the room. So, I think we got to be practical and open-minded. For one, me personally, I would say whatever can enhance the interaction. So let's draw a boundary. Everybody declare whatever you have pre-competitively, and then we walk into the room, and then we find some way to stay as long as we can. And then at some point, people would say, I cannot be in this room anymore. This is getting into competitive level, so I got to get out. But rising tide lifts all the boats.
Okay, thanks.
Thank you. Well, I have to say, yes, please, one more.
Last question, maybe? Go ahead.
Thanks for your wonderful talk. I have a question about with the recent advance of the quantum computer, how will that impact the semiconductor in 10 years?
Yeah. Well, great. I'm already talking about things I have no idea what I'm talking about. So now I'm gonna double down on that. So again, I'm far away from expertise in quantum. Again, I've been taught to some degree by my colleagues. I do see, first of all, depending on exactly what I mean by quantum, some of the quantum technologies is already in deployment right now, and then there are others that's way out there. We don't even know how to put the time scale to the development cycle. But so in between, there's a broad swath and a spectrum, what you mean by quantum. But at some point, I think you got to probably bifurcate. On the one hand, you're going to go physical scale smaller and smaller. On the other hand, you're going to do architectural innovations to derive value and sustain the Moore's law or any other patterns, right? This way going down requires new physics, and this way going requires sort of new mathematical framework, if you will, or design thinking framework. So while I do not pretend to know enough about the future interaction of quantum versus microelectronics, I do think that as, for example, we were showing this chart here, how do you keep growing like that? At some point, it costs so much at this yield, at this scale, to be splitting atoms almost. And then you say, maybe I zoom out, I do 3D packaging and heterogeneous integration, and I do it at that stage to derive similar values. So that's sort of out-of-box creative thinking away from breaking physics into breaking design, breaking in a good sense of the word. So I think we're going to see a bifurcation in both. What's uniquely defining semiconductor industry, however, is not just the technical advances, but their ability to translate it into speed and scale. High enough yield at a cost-effective threshold at large scale. Right? I mean, that is a very unique thing compared to at least today's quantum world. So how those two worlds could intersect, that's going to be hard to see for me. But I can see the bifurcation portion, and both branches will be useful in their own right. Now, I do want to just thank Debasi, first of all, for the invitation to the Armstrong Memorial Lecture again at Columbia. And also, to the Columbia engineering colleagues here, it's been a special treat. I don't get to talk without mentioning budget issues. I guess there was a little bit of that, 50 million here and there, for an hour and a half most of my work days. But I do have to highlight and emphasize perhaps my very first talk for a whole hour long that I really had no idea what I was talking about. I'm purely a messenger carrying the message of what my colleagues and students have been doing. I've done exactly nothing in everything you saw, and I'm just glad that we've got great colleagues at Purdue, and you've got great colleagues here at Columbia Engineering as well. Thank you again.
Thank you. That's fantastic.